covering section 3.9, and it's going to be related rates. So related rates is like pretty weird at first to get used to, and it's definitely like a bit more of a calculus thing, a bit more applied thing. So, I think you might struggle with it a bit, but that's okay. Like these problems are hard, but we'll get through it. So, the question first is like, what even is related rates? Like, what does that even mean? So, like, think about like if we just take a pool. And, I'm just going to draw like a rectangular pool. You can pretend that's a pool for me guys, right? And let's just say, we're, this has like side length L, this has side length W, like as length L, width W, height H. And then, let's just say it's got some water in it, not all the way full. So like, let's just say that total height of the water, let's just say instead of calling that H, let's just actually call the height of the water H. Because, we don't really care about this total height, not yet, not to what we're doing right here. But let's just say, we got a garden hose. I think they're green, I don't really remember to be honest. I haven't seen a garden hose in a while. But, we have a garden hose, we're filling up the pool with water. So, what is happening when we do that? So, we're adding water. And, to add water basically just means to increase the volume. So we're increasing the volume. That's because that's just kind of how it is. You add 2 gallons of water, your volume is now 2 gallons more. But if we look at a pool, like this side is fixed, this side is fixed. So the only thing left that could change, or the only thing that, we're allowing to change in this scenario is that H. So we increase the volume, thus, H has to increase with, or like the height of the water. And that's kind of the idea behind related rates. You have one thing changing, and you want to know how you can use that to like measure how something else changes. Because we do have formulas for the situation. So like the idea here that we're going to be doing is knowing how one, rate of change in one quantity, in terms of like the other. Like, how can we measure one change of one quantity? Which is going to sound a bit more abstract, but when we get through more concrete examples, you'll kind of see what I mean. So basically what's the question is, how does one quantity change with respect to another? That can, be easily measured. So, what I meant by measure it is just like, in order for us to really figure out what this height is, we would probably have to go in, maybe you don't know, like, and maybe no one just knows how deep their pool is. I feel like it's common knowledge though. But, we could probably easily figure out how much water is really being poured out. We could just take like a bucket, or take like an empty gallon of milk, pour some water in at full blast, and just, measure how long it takes to, fill up that gallon. If we know how many gallons of water, if we know like, all this information, then we know like, the length and the width, then we can, that's because it's not very hard information to find. Like, let's just say even if you don't know, you could probably just like, pull out a tape measure or something and just figure that out. So it's pretty easy to just like know how fast like how much water you're adding to the pool, and you could already know like the sides. But if you want to know how long it filled up, you could use these related rates problems to actually, figure that out. Because every time you add water, the height will have to increase as well. Because that's just what it means to fill up a pool. And that's kind of like the problem that we're doing is, how does the height change with respect to a change in the volume? So our goal is to find a relation that connects these two quantities. So we want to put them in terms of an equation. So this one for us will be V, the volume of water is equal to, the length times width times height. And the thing is, though, it's when we add water, we add say 2 gallons a minute. Say, you add 2 gallons a minute, 2 gallons a minute, to the pool. And, what that really means, though, is that you're adding, what that really means is that you're basically increasing the volume of the pool by 2 every minute. And of course, it's not every minute I'm just pouring a gallon in, but this is a nice, smooth increase. So this means it's changing. So this right here is our volume. When we measure volume, it's going to be our volume. And you can say your, delta V over your change in your minute. Well, not every change in a minute. But, if you're adding 1 gallon per minute, this is your volume per time. So really that's delta V over delta T, but not really delta V delta T, but really dV dt. Because what's happening is we're every second, every single moment of time, we're adding water. So the thing is that when we talk about how one thing changes with respect to another, we usually talk about it in terms of time. We don't really need to use time. We can use another variable if we like. When we do more abstract stuff, we can keep it more, abstract. But in terms of the problems that we're going to be doing, we're mostly going to be talking about time. So the idea is, we add water to the pool, so that the volume is going to be increasing. But, that's going to be a function of our time. So, and as we said, as the height, as the volume increases, the height has to increase as well. So that means our height is also a function of time. So, that means dh dt is a value that is, pretty interesting too. Well, not pretty interesting, but, that's non-zero, I should say. As in, it's actually changing. So our goal, in terms of these equations, how can we relate dH dt, so what we want, in terms of what we know. So that was dV dt, so what we know. So in this case, I'm talking about a specific example, but the idea is, we have one quantity changing, you have a relationship with, another quantity. You change one thing, how does it change the other? And in this case right here, dV dt, dV dt, dH dt, it's all going to depend on this equation. So I'm going to move on to a different example that's actually going to be more concrete than what we're doing. But you know what? Let me just finish it real quick. If we take, volume, if you want to take a derivative with respect to time of this whole equation, what we're going to get is, let's see, d of t. So it's going to be V is equal to L times W times H. But really that's just, equal to the derivative being applied to everything. That was just bad notation. So d of dt of V times d of dt of L times W times H. So that tells us is that dV dt is equal to L times W times dH dt. Because L and W are just constants, they're not changing with respect to time, so we get this relationship right here. So we just, divide over by LW, and then if we know how dV dt is changing, then we know how dH dt is changing. And that's kind of the goal, basically create these equations that tell us these things. So, again, this is not like a really concrete example, this is just kind of give you like a sketch. So then now let's actually do a concrete example. One with numbers and stuff, equations that we can actually figure out. So I'm just going to go ahead and write out the problem. So we have the radius of a sphere is increasing. It's going to be increasing at a rate of 4 millimeters per second. And we want to know how fast is the volume increasing. And the thing is, though, it's like volume is also like kind of dependent on the radius, so we also have to specify what value of the radius we want to know. So that's our question. How is the volume increasing when the radius is 40 millimeters per second? So, the reason why we specify the radius is, you'll kind of see what I mean in a second. Because, when we talk about derivatives, formally we talk about derivatives at a point, and we can't, not specify them at a certain location. If we just say, derivative anywhere, then we need some unit of time. You need to tell me what time are we changing. In this case, our radius is going to be the thing that's going to be changing. So as we had time before, here will be our, our radius. Oh, nope, no, I'm done. This is still going to be your seconds. I was thinking about something else. All right, so the question is, what is our given info? Let's do some analysis on the problem real quick. So, what information does the problem tell us? It basically says the radius is increasing at a rate of 4 millimeters per second. So what that means is that dr dt, so r is going to be the radius, is 4 millimeters per second. So, and what is going to be our unknown? What is the thing that we want to find? I'm going to use blue for that one, is how is the volume increasing when the radius is 40 millimeters? So what is dV dt? Let's say when r is equal to 40 millimeters. So one of those key things about these problems is just kind of knowing what is really going on, being able to read it. Like the fact that the radius is increasing at 4 millimeters per second, that means that the derivative of the radius is equal to 4 millimeters per second. If we look at the volume and how it's increasing, then that's basically saying, okay, if volume is increasing, then that's going to be dV dt. And when the radius is 40 millimeters per second, just means you specify a certain time. Well, a certain value of the radius. So how can we relate these two quantities is we look at just the volume of... Wait. Oh, I'm so dumb. It's the radius of a sphere. I think you guys might have... I can't believe I just missed that word. I think you guys maybe have got that, but you know, because I was talking about radius, but I've also could have easily been talking about like a cylinder. So my bad. I was like, did I mention a sphere? Okay, so we're doing a sphere, just in case it wasn't clear. So we have the radius of a sphere is increasing at a rate of 4 millimeters per second. And we want to know how the volume of the sphere is increasing when the radius is 40 millimeters per second. So what is the volume of a sphere? So first off, it's going to let V equal to the volume. And the last thing we're going to do is, you know, we already said it, but R is going to be the radius. So I should probably have mentioned that the info that you typically choose to write, you know, given info and unknown info, is you typically would write, you know, this and this. But that's just because, like, you kind of want to make it clear of, like, what things are. Because you also don't need to state your variables to begin with. I just did these variables because I'm nice. So really, you could have done dv dt is equal to 4 millimeters per second, where your v would be equal to your radius, but you know that doesn't matter so much. So, you know, I'm just gonna put in this little header right there, or like in parentheses. This is like declaring your variables. And, you know, basically what this means is that, you know, now that we have that, our given info and our unknown info basically comes into what I already wrote. So this is kind of what I mean by, like, really the given info here would be like the radius is increasing at a rate of 4 millimeters per second. And, you know, our unknown, which is basically like, you know, what is the rate? Not the rate. What? How is the volume increasing? Or, yeah, okay, sorry. The unknown is the rate of increase. I need to be a bit more precise. It's always rate. All right, okay. So, you know, again, kind of like what I just underlined, I just rewrote just to make it more clear, because once we declare our variables is really what we can write down what I previously had written. Which seems a bit confusing, but, you know, I kind of want you guys to see how I think about the problem as well. But I also need to make sure it's clear for you guys first. So, you know, we know how things are changing. We, you know, label some stuff. So the given info, like I said before, was that we have dr dt is equal to 4 millimeters per second. And our unknown, you know, as like I already said before, that's going to be like, what is dv dt when r is equal to 40 millimeters. All right, so, you know, so far it's not so bad. But, you know, let's keep on going. So the thing is, like, you know, again, we need to relate them somehow. We need to write the volume in terms of the radius, or vice versa. But we do have a relationship for that. We actually do know the volume of a sphere. You know, like, you know, volume of a sphere with radius r. Where v is equal to 4/3 pi r cubed. So that's the way we can, like, actually talk about, the volume in terms of the radius is given by this kind of equation right here. So the thing is now, it's like, we have the rates though as functions of time. So we need to find this equation with dv dt in it. So we need to change this. And what I mean by change is we need to differentiate this equation to get the desired values. Because if we say our volume and our radius are functions of time, then when we take a derivative with respect to time, kind of like what we did with the pool, then what we get is, dv dt is going to equal to 4/3 pi, and then it's going to be 3r squared, which I'm just going to go ahead and simplify a bit. It's going to be 4 pi r squared. Oh, and oops, I forgot something. It's going to be dr dt, because that's the chain rule. So it's going to be 4 pi r squared dr dt. And the reason for that is because, again, like, remember when we had implicit differentiation, when we had, like, y cubed is equal to x, and we want to find dx dt? Well, dy dx. Remember, you'd have to treat this by the, as like a normal derivative, and we'd have to multiply by the, like, derivative of the inside, but the derivative of the inside is y, so it'd be like dy dx. It's basically the same situation. So, what that tells us that, overall we have dv dt is equal to 4 pi r squared dr dt. So, how can we relate this back to what we want now? dv dt. So we have the r, when the radius is equal to 40 millimeters per second, and when dr dt is equal to 4 millimeters per second. So dv dt, whenever r is equal to 40, that's going to be equal to 4 times pi times 40 millimeters squared. You don't really have to write the units. I'm just going to write the units to be a bit clear. Times dr dt, which was 4 millimeters per second. So, this is a section where you just, plug it into a calculator, and you just get 25,600, and then you would want to keep all your units together. So millimeters squared times millimeter is going to be millimeters cubed, and still divided by seconds, and that's after a change in volume. So in this case, the volume is increasing at a rate of 25,600 millimeters cubed per second when r is equal to 40 millimeters. All right, so let me just kind of walk through the problem again one more time. Basically what we had was, we had a radius, like we had a sphere, and we were increasing the radius, and we wanted to know, like, we were increasing the radius as a function of time. We said it was 4 millimeters per second, and the question was, how does the volume increase as the radius increases, and at the specific, and specifically when the radius is equal to 40 millimeters per second? Well, when the radius is equal to 40 millimeters, my bad. And again, this is kind of the reason we have to specify a bit, like, what time are we talking about. or what value we talk about, because when we talk about derivatives we have to talk about a point. So at the point that we're using is the radius is equal to 40. So what we did next was kind of rewrote what we had, the given info and what we want, like our unknown. Then we declared our variables. So we let v equal to the volume of the sphere, we let r equal to the radius, and then we kind of rewrote our info, like our information, what we want in terms of our new variables. So that was like dr dt is equal to 4 millimeters per second. dv dt, is going to be our unknown and what we want to know, and the question is when, r is equal to 40 millimeters per second. And then we know the volume of the sphere, so we just use the volume of the sphere to get the equation that linkage between v and r. The rate of the change in velocity. Well, the rate of change of the volume, my bad. I think velocity. But how does the volume change with respect to the radius? So given that equation, we actually can use that. So we took a derivative of everything. So we differentiated with respect to time. So what we got was, d of dt of v is equal to d of dt of 4/3 pi r cubed. So we get dv dt, the change in volume is equal to 4/3 pi 3r squared times dr dt. Because the fact is that, we really have v of t and we have, r of t. Because our volume and our radius are really functions of time. So once we took the derivative, we got dv dt is equal to 4 pi r squared dr dt. And then we just plugged in the known values we have. That way we could evaluate the dv dt at a specific r value and then just solved. So I'm just going to go ahead and write down the steps of that. In this case I didn't draw a diagram because I didn't really need to. But I'm going to write down the steps so it's a bit more clear. Or not the steps, but, problem-solving strategy, like the way you would want to do it. So the first thing you said, like you want to do is like kind of like what I did with the pool problem is, first off, you need to read the problem carefully. You want to do that way you kind of know what things are changing, the way you can get your information that you have. You want to be able to understand the problem in a way that basically tells you exactly what's happening. Because in math, we don't add extra words, we don't add anything less than what you need, you add exactly what you need. So you have to make sure you understand the problem and understand, what exactly is it saying. So, now in terms of the pool problem, the thing that we did was we, draw a diagram if possible. So, one of the things we say in math, draw a picture if you can. It's always helpful. Like, in terms of the pool problem, it's pretty nice. And, there's some other problems which we'll do. Like, I'll do, I think, 2 more examples, and then you'll see, I'll draw pictures for some of them, because it's just helpful to understand what's going on, and it's helpful to set up the equations. Because sometimes it's not very clear how things should be. Especially if we get into, changes in angles, where then we need to know the sine of the theta, but we need to be able to identify those pieces on a triangle. So, after we draw a diagram, after we read the problem, we need to introduce notation. So what this means is, we assign symbols for all the quantities that we know, but specifically to all quantities that depend on time. That way, you know, like what we did with the previous problem, we had, you know, the change of velocity, so, you know, dv dt, or, you know, we like let v equal the radius, well, no, v is equal to the volume, r is equal to the radius. And then we have to express, you know, the given information that we want in terms of those, you know, in terms of the new symbols that we created, or the new notation. All right, so once we express the given information, we want to write it in terms of, you know, derivatives. So what we wrote once we had, you know, what our velocity, or not velocity, where our volume was, you know, we wrote that, you know, we wrote that, you know, we said, you know, v is equal to the volume, r is equal to the radius. We changed what our given info was. So our info in terms of the new variables was dr dt is equal to 4 millimeters per second. And then dv dt whenever r is equal to 40 millimeters per second. So basically this little portion right here just basically means turning it into math. So the next step is going to be, we want to write an equation that relates to quantities. Or not even just two, just, you know, their desired inequalities. So write an equation that relates the various, I need to make sure to use proper wordage. I think that's I don't even know that's the correct word. Quantities. So basically what this means is, you know, if you have like, you know, you have the two variables that you want, or like, you know, typically it's two, sometimes there might be more, there might be 3 or 4. You can really complicate it if you really wanted to. It really depends on the situation, but for us, we're not going to do anything too complicated. So typically it's 2, but, you know, we want to find an equation that links them, and sometimes you might have to use geometry. And the last part for 6, the last part, 6 is going to be, second to last part, I should say. We use the chain rule. Because we use the chain rule to differentiate the equation to get, you know, our rates that we want. So the way we do that is just to differentiate both sides with respect to t. So, you know, basically what we did was, you know, d of dt of our whole equation. Then lastly, what we did, you know, substitute given info. You know, into the resulting like equation. Alright, so my handwriting is a bit messy, but I think you guys can deal. So the last step is going to be, you know, once you take a derivative, you want to plug in all the information that you know, and then just solve for the unknown rate. So let me just go over the steps one more time. So the first thing we want to do is, you know, when we see a problem, read the problem carefully, make sure you understand the problem, make sure you understand what it's being given, what it's asking you to do, and all that. If you can draw a diagram, definitely try to do that. Because sometimes, like, if you need to use geometry, then you'll probably need to actually draw a picture to help you understand what the sine of this thing, like, what is the sine of this angle supposed to be. Or like, the pool problem. So draw a diagram, if it's possible, if it helps, go ahead and do it. It may help you, like, create the equations that you need. Once you do that, you want to introduce some notation and assign symbols to all quantities that depend on time. So basically what that means is just basically math it. Just turn that shit into math. Like, the thing that we did when we talk about volume, like V equal to volume. When we have radius, let that equal to R. If we have, lengths of a triangle, we'll say, A, B, C. Kind of like A squared plus B squared is equal to C squared. Or we could use X and Y instead. The point is that we need to call the values, the quantities that we want to, like, measure and understand, we need to call them something. And specifically what we want to do is really label the ones that depend on time. So that way, they kind of stick it out in our mind that we know when we take derivatives of them, we talk about them in terms of time. So once we label everything, we just take our given information and what we want to know, we just turn it into math again. So for us, that was, dV dt is equal to dr dt is equal to 4 millimeters per second. And then that the rate of change in the volume was that was equal to dV dt. And the last few things that we did was basically just okay, now we have these two things that we want. We have one thing that we know, one thing that we don't know. We need to link them by some equation. So we created that equation that basically relates all the quantities that we want or that we have. And sometimes we want to use geometry when necessary. Again, if you need to use geometry, probably draw a picture, that would definitely help. The last thing we did was, but then we, once you have that equation, you use the chain rule with respect to time. So take a derivative of everything with respect to time. Because typically that's the one you use. If it's another variable, I'm sure it will probably say it or it'll be obvious. And then, once you take a derivative with respect to time, just plug in all the information that you have, solve for the unknown rate, and then, that's the problem. All right. So this last example, I'm going to try to go through it kind of quick. Well, like I said, I was going to go through two more examples. So a ladder is going to be 10 feet long. And we know it rests against the wall. I should say a vertical wall. Did I really spell vertical wrong? I did. And we know if the bottom, let's just say the ladder is slipping. So if the bottom of the ladder is moving away from the wall, in this case, slides. So let's just say it's doing it at a rate of 1 foot per second. Then the question is, how fast is the top of the ladder sliding down the wall from the bottom of the ladder whenever it's 6 feet away from the wall? You know what? No, that's not a good one. I don't like that one. So we have this information, and what we want is, how fast Okay, yeah. I'm gonna write it down first, and then I'll say it. All right. Bottom. All right, so sorry about the, blank moment in time, but it's a lot to write. And also just hate writing. I write slow. That's why whenever I do see these problems, I just immediately turn into math notation because I'm lazy and I write slow. But, that's kind of like besides the point. All right, so I write in 2 different colors too, so you guys will love that. So basically what's happening is we have a ladder that's 10 feet long. So, that rests against the vertical wall. So I'm going to go ahead and draw that picture. I'm going to use black. So let's just say that's your picture. Vertical wall, we'll assume it's perpendicular to the ground. And, we have a ladder. Let's just say it kind of looks like this, and we'll assume it's a bit crooked. So let's just assume that's our ladder. So we have a ladder, 10 feet long. So this length right here will be 10 feet. That's the length of the ladder. And if we know the bottom of the ladder slides away from the wall at a rate of 1 foot per second, well, we need to say, let's say this right here is the bottom of the ladder, and this distance right here will be from the wall. So we'll call this distance x because we need to call it something. And the question is asking us, how fast is the angle between the ladder and the ground? So this angle right here. How fast is that changing, or what is the rate of change between, for that angle? And specifically when the ladder is 6 feet from the wall. So x is going to be the distance, from the wall to the bottom of the ladder. So theta is going to be the angle between the ground and the bottom. The angle between the ladder and the ground. All right. And just kind of clarify what the motion is doing is that we have, the ladder slipping away. Because of that, this thing is basically this is going to be sliding down. But basically what this means is that this angle right here is going to be decreasing. So that's going to be our d theta dt. So that's what we need. But, let me just kind of clarify what our goal is and, what our information is. Oop, I gotta sneeze. Oh. I guess I didn't need to sneeze. If I just randomly sneeze in the middle of this, guys, I am so sorry. Okay, sorry. Let me just go back to the math. So, again, what's happening is, we kind of need to talk about our variables, is that, our given information is that, the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So, the distance that we had, the length between, the bottom of the ladder from the wall, we said that was x. So that information, what that tells us is that dx dt is equal to 1 foot per second. And the question was, what is d theta dt? And, let me just kind of clarify. So what we want to, well, not what, but we want to find d theta dt when x is equal to 6. So whenever the bottom of the ladder is 6 feet away. So, in terms of trigonometry, we can actually relate this. So how can we relate, an angle to this side and this side? That's just a cosine. So we have, cosine of that angle. I'll say using trig. Cosine of that angle is equal to the opposite, well, not opposite, is equal to the adjacent, so equal to x, divided by the length of the ladder, or the hypotenuse, so divided by 10. I'm not going to use any feet or anything like that for right now because it's just tedious. And then the last thing we have to do is, actually differentiate now. So we're going to take the derivative of everything, this whole equation. Cosine of theta is equal to x over 10 with respect to time. What we're going to get is, negative sine of theta times d theta dt. Because remember, this is basically like the chain rule. You have to multiply by the derivative of the inside. You get sine of theta times the derivative of theta, which is d theta dt. Then what we get over here is 1 over 10 times, let's see, remember the derivative of x is just, dx dt, because in this case, x is a function of time, so we just get dx dt. So that's what we get is d theta dt is equal to negative 1 divided by sine of theta times 10 times dx dt. Now the thing is we don't know what theta is, but we can solve for what, sine is. So if we look just back at the triangle real quick, I'm just going to draw a rough sketch. This was our angle theta. This is equal to 6. This is equal to 10. So if this right here is our y, then we know y is equal to this square root of 10 squared minus 6 squared. Because, basically we have is x squared plus y squared is equal to 10 squared. That's just Pythagorean theorem. We can use that to solve for y. And what we get is just, I think this is 8 is equal to the square root of 64, which is equal to 8. So that is equal to 8. So once we solve for that triangle, we can basically solve for that sine of the theta. So we get sine of theta is equal to 8 over 10, which was just equal to, 4/5. So basically all I did was okay, well, take the given information. We know things about triangles, use a bit of geometry, and then from there, we can just solve for the rest. Well, but from there, we can solve for the unknown value in our equation, which was sine of theta. So now we can just plug that in. You get d theta dt equal to negative 1 over 4/5 times by 10 times, remember dx dt was 1 foot per second, so times by 1. That's just going to be equal to negative 1 divided by, let's see, 4 times 10 is, well, really it's just 4 times 10 divided by 5. 10 divided by 5 is 2. 4 times 2 is 8, so negative 1 over 8. And let's just do some algebra to double check that if you want. So what that theta is, d theta dt is going to be equal to negative 1 over 8 radians per second. And you could say degrees if you want. But typically when you talk about sines and thetas like that, typically we talk about them in terms of, theta, so that's what you want to keep it as. So what this gives us is that the rate, or like, not the rate, but the angle is decreasing. Actually, the angle is actually decreasing. And we'll say at a rate of 1/8 radians per second. So, even though I wrote, the answer was -1/8, I wrote the fact that it was decreasing. Oh, I did not write it was decreasing. I am dumb. Okay, sorry. So, well, I just turned it back into words because it's what I like to say is like if you do a word problem, then your answer should be in words, so not in terms of math. And again, what this problem was, we had a ladder that was 10 feet long, resting against a vertical wall. I drew the picture along with it, and it said the ladder was sliding away, so that's how we got that X. And then because of the fact that the ladder is actually slipping down, it's also like moving down in the Y coordinate, but really what that means is like the height of it. Really what that means is the angle is decreasing. So how does that falling away change the angle? Well, we use the distance from the wall to the ladder as x. We use the the theta we set the angle is equal to theta. We put that in terms of the equations that we know. So dx dt is equal to 1 foot per second because that's what it's stated in the problem. Our goal was to find d theta dt is equal whenever x is equal to 6 feet per second. And then we use trig, just trigonometry or whatever you want to call it, to just work out the the relationship between theta and x. So we just got cosine of theta is equal to x over 10. Well, x over 10. Remember, theta and x are functions of time, so we took a derivative with respect to time. And this is, we basically found a way to get d theta dt as a function of like dx dt. We needed to do a bit of math to figure out what the sine of the theta is. And so, that's to be expected in some of these problems. So once we figured out what sine of theta was, we just plugged it in and we got our answer. So it's not really it's a bit tedious at first, but I wouldn't worry about it too much. Because, while it's a bit tedious and annoying, it's not it's not hard. You just have to really take your time. It takes a while to get used to these kind of things. And it just takes a while to get used to these kind of things. So if you struggle with it a bit, that's okay. You just have to get used to the wordage. I don't know what the word is. It just takes a while to get used to it, but that's fine. I said I was going to do 2 examples. I'm just going to do one quick thing that's kind of on the homework. I think what I was going to do was question 14, which is the very last one. I'm just going to do it with some numbers. I'm not going to solve it, but I'm going to just help you guys understand what's happening. So basically what's happening is it says when air expands adiabatically, without gaining or losing heat, its pressure and volume are related to by the equation PV is equal to 1.4. So we have air, we have air expanding. We have the pressure, heat is the same, temperature is the same. And we have the equation PV is equal to P to the 1.4 is equal to some number C. where P is equal to our pressure, V is equal to the volume of the gas, and we don't know, like, we know that, dV dt, what the problem says is that suppose at a certain instant, the volume is increasing at 500 centimeters cubed. And then I'll say like per second, I guess. And we know the pressure, when it, basically we know it's changing, that the pressure is 80 kilopascals, I think is what it is. Oh wait, no, I'm dumb. It's not that dV dt is equal to that. Oh, I'm dumb. It's that the volume is equal to 500 centimeters cubed. Well, 500 centimeters cubed. So basically it's saying, suppose that at a certain instant the volume is 500 centimeters cubed, the pressure is 80 kilopascals, and is decreasing at a rate of, we have dP dt is equal to negative 10 kilopascals per minute. All right, I read through the problem, but my brain just kind of forgot what it was doing for a second. So the question is, like, what is dV dt? So basically we're saying is, okay, well, we have air that's going to be expanding. It's going to be not losing or gaining heat, and we know that the pressure and the volume, PV to the 1.4 is equal to C, which is not the typical form of the equation I see. But we know that's constant, so we have this equation relating to them. Then we suppose at some point of time the volume is equal to 500 centimeters cubed, and that pressure is equal to 80 kilopascals at that moment as well. And then the question is, also at that moment, the pressure is decreasing at a rate of 10 kilopascals per minute. So basically this was you're given information, and the last right here is what we want. Now I'm not going to solve it for numbers because I'm just not going to bother with that. I'm just going to helping you guys kind of understand what the problem is, and hopefully this helps too. But, what is dV dt? Well, we got to look at this equation. P times V is 1.4 is equal to C. You have to take a derivative with respect to time. So really what that kind of gives us is that, this is actually going to be a product rule. So I'm just going to go ahead and, rewrite that. Because, d of dt of a constant is equal to 0 because constants don't change. So this will be dP dt times, v to the 1.4, because this is going to be the product rule. Because really, again, it's P of t times V of t to the 1.4 plus then 1.4 V to the 0.4 times dV dt is equal to P. Well, times P is equal to 0. And the reason for this is because, it's a product rule. I just use the chain rule appropriately as well. And I'm just going to solve for dV dt. So move this term over. So that's going to be negative dP dt times V to the 1.4. And then we have to divide by this. We'll divide by everything else. So divided by all this stuff right here, everything else attached to the dV dt to get 1.4 V to the 0.4 times P. So this will be equal to, let's see, negative dp dt, the v to the 1.4 and the v to the 0.4, those are just going to give you the v to the 1, so just v, divided by 1.4p. And that's basically the answer. You just have to plug in the information you have there, and then that's it. Alright, yeah, so this problem is a bit weird, but that's basically the idea. I wanted to just show you how to construct the problem real quick, and why you would have to do, help you understand that's going to be the product rule. But that's it for this section. Like, comment, and subscribe, I guess. If you want me to go any more examples, if you have some issues with the homework, feel free to email me. And I'll basically just set up time to come help you out. I don't mind. But alright, thanks for watching. Peace out.